Hello everyone, I am Tuhinur Rahman, lecturer of physics, Cambrian School and College. I hope you are all safe and sound. Welcome to today's physics class. Now, today I am going to discuss about some of the units and dimensions of the quantities regarding chapter 7, which is the structural properties of matter. By the end of the lesson, you will be able to determine the unit and dimension of viscosity coefficient, determine the unit and dimension of surface tension, and last but not least, at the end of this lesson, you will be able to determine the unit and dimension of surface energy. But if you want to understand today's topic first, the things you need to understand first are the fundamental quantities, units of fundamental quantities, and the dimensions of the fundamental quantities. Now, there are 7 fundamental quantities that we are going to discuss because it's going to be necessary for all the units and dimensions for the later stages of any quantity in physics. Okay. First, we will write the quantity, then their unit with the symbol and the dimension. Okay. The first one is, as you know, its length, but we will not only consider length. We can also take breadth, width, diameter, thickness, everything that can be measured in length. It has a unit of meter and the symbol is m, and it has a dimension of L. As you can see, the first letter that I highlighted is the dimension. The second one is the mass, and we measure mass in the SI unit as kilogram, and we can write its symbol as kg, and it has a dimension of capital M. The third one, as you know, is time. The SI unit of time is second, and we use its symbol as a small s, and it has a dimension of capital T. As you can see, the first letters denote the dimension. Now, in the HSC level and the things that you have learned in the 9th and 10th grade, most of the quantities that we use in physics in the HSC level and the SSC level can be determined by these 3. But there is one that we need to know for the higher secondary level or for your admission test as well, is these are our quantity and unit symbol with the dimensions. Okay. The fourth one is the electric current. We measure it as in ampere, and it has a symbol of capital A, and the dimension is I. Okay. Now, this one is very, very important because I am going to discuss some of the quantities that's going to be necessary for your HSC MCQ and admission test as well, which is the temperature. Okay. Temperature, we measure it in Kelvin scale. Okay. It has a symbol of capital K, and this is the most important part. The dimension of temperature is theta, but this cannot be said as just theta. We will call it as the uppercase theta. Okay. This is the uppercase theta. And the 6th one is the amount of substance. We use the SI unit as mole, and the symbol is MOL, the first 3 letters, and it has a dimension of capital N. And the 7th fundamental quantity is the luminous intensity. It has a unit of, as you know, candela, and its symbol is CD, and it has a dimension of capital J. As I have said in the previous slide, the 3 things, M, L, T, are going to be necessary, and from this slide, the uppercase theta, which is the dimension of temperature, will be very important for your HSC level MCQ and your admission test as well. Now, I am going to go from the basic. The first one is the unit of velocity. As you know, velocity is defined as displacement per unit time. So, we can write V equals S by T. S has a unit of M and T has a unit of S, so it has a unit of meter per second. You all know that, it's easy. If you can determine the fundamental unit of velocity, you will be able to determine the dimension of velocity. Similarly, velocity equals S by T. S has a dimension of capital L because we measure displacement in meters, and T is time, so you can write capital T. So the dimension of velocity becomes LT inverse 1. Okay, you need to know, if you know the dimension of velocity and the fundamental unit of velocity, it will be necessary for the latest stage of the video because we will use LT inverse 1 in case of velocity. Okay, directly, we are not going to discuss it again and again. And the next one is the unit of acceleration. As you know, acceleration is defined as velocity per unit time. We write velocity as S by T, so this equation becomes A equals S by T square. So the unit is meter per second square. In the later stage, when we are using acceleration, we will directly write meter per second square. You all know that, you have learned it in the 9th and 10th grade. The dimension, you see, I have shown you this slide and this. A equals S by T square. Okay, so we want to find out the dimension. S has a dimension of capital L and T has a dimension of capital T, so we can write the dimension of acceleration is LT inverse 2. We will use it directly. Now the next part is the fundamental unit of force and the dimension of force. From Newton's second law of motion, we can write F equals ma. Okay, m is the mass. As you know, the SI unit or the derived unit of force is Newton, but we do not want to write the unit of force in Newton because we want to find out the fundamental unit. So we write as Newton equals kg meter per second square. As I have said, I will use the unit of acceleration as meter per second square directly, which I have done here. Mass has a unit of kg and acceleration has a unit of meter per second square. So Newton, whenever we are trying to write force, we will have to we can write actually kg meter per second square. So if you can write the fundamental unit, I think you will be able to write the dimension of force as well. As force, the dimension of force is m LT inverse 2, which kg is substituted by capital M, small m is substituted by capital L, and S is substituted by capital T. I think you will be able to understand this. The fundamental unit of work, as you can see, that definition of work is force into displacement. So we write it as W equals ms using the Newton's law as F equals ma. So as you know, the unit of SI unit of work done is joule, but joule is a derived unit. We want to find out its SI units or the fundamental units. So mass is kg, acceleration is meter per second square, as I have said at least 3 times, and S is meter. So these equations become kg meter square second inverse 2. This is the fundamental unit of work done, which is joule or kg meter square second inverse 2. If you can write the fundamental unit, I think you will be able to write its dimension. The dimension of work here, as there is another way you can write that. If you know the dimension of force, you will be able to determine the dimension of work as well, as F equals ma, and we can write MLT inverse 2. We substitute the values of F and S here as W equals MLT inverse 2, which is the dimension of force, and S is L. So we can write ML square T inverse 2, which is the dimension of work done. In the latest stage, I am going to use the unit and dimension of force and work done directly, which is force is MLT inverse 2 and work done is ML square T inverse 2. If you can remember it, right, I think it will be easier for you to solve all the units and dimension, and it will save you some time in the MCQ in admission test as well and in the SSC level as well. So our main topic today was the unit and dimension of viscosity coefficient. As we can see, we can write Newton's law of viscosity as F equals eta A dV by dy. We want to find out the unit of eta, so we can write eta equals F division A dV by dy. So eta equals force as a unit of SI unit of Newton, area is meter square, velocity is meter per second, and dy, which is the thickness, as we can write as meter. This meter and this meter, they get vanished, and this meter square, it gets up, and S inverse, it becomes S. So it equals Newton second per meter square. If you can recall, pressure is defined as P equals F by A, right? That means force per unit area, and it has a unit, SI unit of Pascal, which we can write as Newton per meter square. So we are going to substitute Newton per meter square as Pascal. Okay, so this eta equals Newton second per meter square becomes Pascal second. So we have found two units of viscosity coefficient. One of them is Newton second per meter square, and the other one is Pascal second. But there is another unit which was named after the famous scientist Poiseuille. According to his name, we will call it just Poios. Okay, so the unit of coefficient of viscosity is Poios or Pascal second or Newton second per meter square. Now there is a fundamental relation between Newton second per meter square or Pascal second with Poios. Poios, this is the relation. This is going to be very necessary because this is asked frequently in the SSC level MCQ and medical admission as well, as 1 Newton second per meter square equals 1 Pascal second equals 10 Poios. Okay, this is very important. Now the dimension of viscosity coefficient. Newton's law, so eta equals F divided by A dV by dy. As I have said, I am going to use the dimension of force directly, so we have written force equals mLT inverse 2. Area is L square, velocity is LT inverse 1, and thickness is L. So this L and this L, they get vanished. This L square goes up and this T inverse goes up. So the dimension of viscosity coefficient becomes M L inverse 1 T inverse 1. This is very, very important. Now the next topic is the dimension of surface tension. As you can see or recall, if you can recall the definition of surface tension. Surface tension was defined as force per unit length, right? So we wrote T equals F by L. F equals MA, and F has a dimension of MLT inverse 2. So we can write as MLT inverse 2 by L. This L in the numerator and the denominator part, they get vanished and it becomes T equals MT inverse 2. Okay, this is important. Now the unit of surface energy, E equals W by dLA. Okay, so work done has a unit of joule, SI unit per meter square. So the unit becomes joule per meter square, but we want to find out the value of joule. So we can write as W equals Fs, W equals Ms, or joule equals kg meter per second square into meter. So it becomes joule equals kg meter square second inverse 2. We substitute the values of work done here and meter square as well. This meter square and meter square, they will disappear, and E equals kg per second square, which is the fundamental unit of surface energy. Okay, this is important. Now the dimension of surface energy. If you can recall, E equals W by dLA. Work done, as I have said, you can use it as ml square T inverse 2 directly. It will save you some time, but for W equals ml square T inverse 2, we substitute the values here, ml square T inverse 2 divided by L square. So the 2L square in the numerator and the denominator part, they negate each other. It becomes E equals MT inverse 2. Now, can you recall what is the dimension of surface tension? Yes, the dimension of surface tension is MT inverse 2. So it can be said fairly that the dimension of surface tension and the dimension of surface energy are same. Okay. These two are very, very important. Now, this is time for evaluation. Okay. The first one is, what is the unit of viscosity coefficient? I think you will be able to answer. One of them is Newton second per meter square, the other one is Pascal second, and the third one is Poisson. These three are very, very important. The next question is, what is the dimension of viscosity coefficient? If you can recall, it's L inverse 1, T inverse 1. The next question is, what is the unit of surface energy? You can write as joule per meter square. Now, what is the dimension of surface energy? It's mt inverse 2. Okay. Next question is, what is the unit of surface tension? Surface tension has a unit of Newton per meter because it was defined as T equals F by L. Okay. Now, what is the dimension of surface tension? It's mt inverse 2. Now, I have kept two questions for you to practice. The first one is, what is the fundamental unit of entropy? Okay. And the second one is, what is the dimension of entropy? I think if you have watched this lecture and understood, I think you will be able to answer it. And this is one of the very important topics in second paper. I hope you have enjoyed my class. That's all for today.